In the previous video, we already derived the spherical harmonics. It is the angular solution of the hydrogen atom wave function. From the eigenvalue problem of L squared, we could obtain the spherical harmonics y, which is the angular solution to the wave function. The remaining part is the radial solution capital R, and in this video, we are going to derive it. Let us start by simplifying the kinetic energy operator. The angular derivative part, which is marked by the rectangle, is equal to L hat squared applied on psi. By knowledge of its eigenvalue, we get the expression where we no longer have angular derivatives. It will be useful to expand the radial derivative into two separate terms. The purpose of this will become clear later. By substitution of the kinetic energy operator into the Schrödinger equation, now we are ready to derive the radial solution. Move the right-hand side to the left and multiply the entire equation by minus 2m over h bar squared. We have a tidier form of the differential equation. We remember the fact that psi consists of the multiplication of y and capital R. By replacing psi with y times r, and knowing that y does not depend on the radius r, we are left to solve the capital R alone. Okay, now we begin the process of solving the differential equation. Let us make some change of variables by defining r1 and epsilon. It will also be good to make a change of variable by defining y as capital R times the square root of r1. We also define s as 2l plus 1. Now we have rewritten the previous equation as the differential equation of y with respect to r1. We are going to solve y first, then return it back to capital R. Let's make further change of variables by defining x and lambda. Use them so that we obtain the equation at the last line. The solution must work for interval where x is very small and where x is very big. For the first region, we demand that y is a polynomial of x. This form of function will certainly approach 0 when x approaches 0. For the second region, we require that y has a decaying exponential form. This way, y will approach 0 when x approaches infinity. Okay, now we have two seemingly separate solutions working separately for opposite extremes. Just combine them both by putting together the decaying exponential, the polynomial of x, and a polynomial function q of x. Plug this ansatz of y into the differential equation of y, and we obtain the differential equation of q. The next line shows the defining equation for generalized or associated Laguerre polynomial. Here, p is defined as lambda minus s plus 1 over 2. Anyway, the polynomial is defined in the last line. Let us use the fact that s has been defined as 2l plus 1, so we can express lambda in terms of p and l. Shift your focus to the table on the right side. There are three operators in the first column, namely the Hamiltonian, square of angular momentum, and Lz. Each operator has its own eigenvalue, and more importantly, the quantum number associated with it. N is the primary quantum number, L the azimuthal quantum number, and M the magnetic quantum number. N is defined as n sub r plus L plus 1. By looking at the similarity between lambda and n, we can express p in terms of n and L. For a given value of n, the maximum value L can take is n minus 1. You can derive this yourself by remembering the fact that p cannot go below 0. The relationship between r1 and x is r1 equals to nx over 2. You can derive this from definition of x and lambda, and also the fact that lambda is equal to n. Putting this into the expression of y, we can replace y with capital R and be ready for normalization. This is the integration that will be used for normalization. The additional r² term is present because the integration is calculated in spherical coordinates. I'm not going to show you the normalization process because it is very tedious, but here is the normalization constant. Now here it is, the complete solution of the wave function, obtained from combining the radial and angular solution. In case you forget, I've added the definition of angular solution y. Expressed this way, the wave function looks somewhat scary. But don't worry, let's see the artistic version of it just right away. The best way to display the wave function is to actually plot the probability density. You can see two cases where I put two sets of n, l, and m. The brightness indicates the likelihood of finding an electron in a particular region. The brighter it is, the more likely you can find an electron in that region. If we change the quantum numbers, we can get fancier results. You see, this is actually the proper way to describe an electron around an atom. Electrons do not orbit the nucleus the way the Earth orbits the Sun. This kind of picture goes by the name of the electron probability cloud. Their structure and symmetry strongly showcase that nature itself is the greatest artist. Alright, we have completed our discussion about hydrogen atom wave function. In case you haven't, don't forget to subscribe so you won't miss the next content. Thank you and see you in the next video.